So my decreasing y values, so if f of x is less than 0 in concave up means that my values of my derivative, my second derivative of f of x has to be bigger than 0. And increasing values, f prime of x has to be bigger than 0, which means f double prime of x has to also be bigger than 0, which means concave up. Concave up is just a fancy way of just saying my graph does this. Concave down means it just goes the other way. There's a downward motion with concavity, which means that it's bending downwards. So graphs that are concave down, so graph lies below tangent lines at each point on the interval. So that means that my second derivative, f of x, is less than 0. So I get m is equal to -1, m is equal to -3. Like I said, guys, we'll do examples where this will make a whole lot of sense. So what does this all mean? How can we figure out when a graph is concave up or concave down? So I want to find the value of the second derivative at x is equal to 2 for f of x equal to 2x cubed minus 12x plus 2. Then I want to determine whether the curve lies above or below the tangent line at this point. So I have my regular function f of x is equal to 2x cubed minus 12x plus 2. And I know my derivative of f of x is 6x squared minus 12. And I also know that my second derivative is 12x by itself. Now I want to find the second derivative value when x is equal to 2, which is equal to 24. And we know that 24 is bigger than 0. So if 24 is bigger than 0, from my definition from the beginning, that means that my graph is going to be concaving up. Okay? So at x is equal to 2, f of x is concave up. Which means f of x is above tangent line at x is equal to 2. Which means if I have my graph, and this is x is equal to 2, at x is equal to 2, my graph is going to go in an upwards motion. Does everybody understand that? Okay, perfect. Again, I'm not going to sketch the whole graph, but if you go on Desmos and put in 2x cubed minus 12x plus 2, at x is equal to 2, you'll get an upward movement of some sort. Now, points of inflection, we've heard about this many, many times. So the point C and f at C on a graph f of x is said to be a point of inflection if the graph is continuous at x is equal to c, which means there's going to be a type of bend. Okay, that's what inflection means, is that there's going to be a bend of some sort. So in other words, this is where the concavity changed from concave up to concave down or vice versa. So like x cubed has two concavities. It concaves up and then concaves down. Okay? So I have f of x is equal to x cubed. Then I have my derivative of f of x is 2x or 3x squared. And then f double prime of x is equal to 6x. So now I need my sine chart. Okay, we know that where does my graph of f is equal to x cubed cross my x-axis? At what point? in normal f of x is equal to x cubed, it crosses the origin at 0, 0. So if I go to the right of 0, if I put f double prime of x at 1, then I get positive 6, which is bigger than 0. So this means that this is concave up. As x approaches my positive numbers, if I put in negative 1 of 6 times negative 1, which gives me negative 6, this is less than 0, which means that I'm concaving down as my x's get closer to the negative numbers, which means that I have concave up from 0 upwards, and I'm concaving down when I get towards my negative x values. Does this make sense? Can you guys tell the difference between concave up and down? Is everybody good with concaving up and down and the definition? Perfect. Okay. So now note that all points of inflection on the graph y is equal to f of s must occur either when the second derivative of f of x is equal to 0, or when double derivative of f of x is undefined. So for example, we have f of x is equal to x 1 over 3. The derivative is 1 over 3 times x to the negative 2 over 3, which can be written as 1 over 3x 2 over 3. And then my second derivative is negative 2 over 9x to the negative 5 over 3, which is the same thing as saying negative 2 over 9x to the power of 5 over 3. So the graph has a point of inflection when x is equal to 0, even though f prime of 0 and f double prime of 0 does not exist, okay, because it's going to give me an undefined point. So if I take my f double prime of x, I know that at 0, my graph is going to be undefined. Okay. However, if I figure out if it's concave up or down, I just have to sub in a positive number and a negative number to my double derivative. So if I sub in a positive number such as 1 for f double prime of x is equal to negative 2 over 9x to the power of 5 over 3, I get a negative number over a positive number, which means that my graph is going to be concaving down. And then I get a negative over a negative, which gives me positive, which means my graph is concaving up. And my point of inflection will happen at 0, 0. So this is basing off f of x. This is going to be 0 to the 1 over 3, which is 0, which means that my graph is going to cross at 0, 0. And as you can see, it is concaving down because there's this downward motion in my positive x value. So this is concaving down. And this is concaving up because you see that nice little cusp that goes up in my negative x values. Thumbs up if you're good with this, yes or no. So in order to determine concavity, you're subbing a positive and a negative x value for your second derivative function. And that will tell you your concavity. Your point of inflection is when you find your y-intercept for your f of x function. Does everybody understand? Okay, perfect. So to determine any points of inflection, find all x values for which the second derivative f of x is equal to 0, or where it's undefined to determine possible points of inflection. Verify that the second derivative of f of x changes signs at x is equal to the critical point. So the double derivative is less than 0, which means this is concave down. The second derivative is bigger than 0, which means this is positive, which is concave up. Again, concave up, and less than 0 is concave down. So now we want to determine the intervals of concavity for which the following functions state any critical points and or any points of inflection, and we want to sketch each curve. So first of all, we need to find the asymptotes, okay? So our vertical asymptote is none, because I cannot factor out my denominator, and I cannot have a negative square root. My horizontal asymptote is then just going to be y is equal to 0. Can anyone tell me why my horizontal asymptote is y is equal to 0? It has to do with the denominator and the degree and all of the signs in that denominator. So will I ever get a negative number? Yep, basically, Priyanshu, thank you. So the limit approaches 0, okay, which means that my whole function will never ever be 0. It will always be above my x-axis. So now if I take my derivative of f of x, I get negative 2x times 1 plus x squared to the power of 2. So now let's try to figure out if there's a local max remaining using our first derivative. So I have to set my first derivative equal to 0. So let's set our derivative equal to 0. So I get 0 is equal to negative 2x over 1 plus x squared to the power of 2. Cross multiply, I get 0 is equal to negative 2x. I get x is equal to 0. So I need to figure out what how my tangents react when I have my tangent at 0. So I'm going to make my sine chart. So this is f prime of x. I know I have 0. To the right of 0, if I sub in 1, I'm going to get a negative number over a positive number, which means negative. And if I put a negative number, I'm going to get a positive number because it gets a positive over a positive. Which means if we're going from positive tangents to negative tangents, is there a max or min at x is equal to 0? Max, okay? This means there is a local max at x is equal to 0. So let's figure out what that max is. So f at 0 is equal to 1 over 1, which is equal to 1. So my max happens at 0 and 1. Okay, so we got that down. So which means that my f of x increases when x is less than 0, and my f of x decreases when x is greater than 0. So now I need to take my second derivative to find out my concavity. So if I take my second derivative, again, I have to use my quotient rule. So I get negative 2 times 1 minus 3x squared over 1 plus x squared to the power of 3. Or you can use, not quotient rule, you can use the product law. You just bring your positive numerator up and make it negative. So now let's check when my second derivative is equal to 0. So I get 0 is equal to negative 2 times x minus 3x squared over 1 plus x squared to the power of 3. I cross multiply. I get 0 is equal to negative 2 times 1 minus 3x squared. Divide both sides by negative 2. I still get 0 is equal to 1 minus 3x squared. I get 3x squared is equal to 1. X squared is equal to 1 over 3, which means that x is equal to plus and minus 1 over root 3. So now I need to do my sine chart over here. So f double prime of x. I have it at negative 1 over root 3. And I have it at positive 1 over root 3. So when I'm between negative 1 over root 3 and positive 1 over root 3, I get a negative number over a positive number, which means that I'm concaving down. If I'm to the left of negative 1 over 3, I get a positive over a positive, which means I'm concaving up. And then same thing with to the right, I am concaving up. So now I need to figure out my 2 points of inflection. I know it's at f prime. I need to figure out f at negative 1 over root 3 and f at 1 over root 3. And they both are going to give me 3 over 4. So my points of inflection are going to be at -1 over root 3 and 3 over 4, and 1 over root 3 and 3 over 4. So I have my -1 over here. I have my 1 over here. Sorry, I should draw them more towards closer to 0. So I got -1 and 1. So I know that I have a maximum at 0 and 1. So this is my max at 0 and 1. And let's say this is 3 over 4, which is over here. So I have 1 and 3 over 4 and -1 and 3 over 4. And my horizontal asymptote is y is equal to 0. So from negative infinity all the way to -1 over root 3, I am concaving up. And then because I'm max, I'm concaving down. Which means that that is what my graph would look like. So concave up, I'm concaving up because I have those cusp over here. That makes basically a little minimum, which is going in an upwards direction. And same with 1 over 3 and to the positive infinities, I have this little upward cusp here, which means I'm concaving up. But at my maximum between -1 over root 3 and 1 over root 3, I have this little hump over here and I'm concaving downwards because my tangents are all going to be in negative value. So I hope that did not confuse you at all. It'll take time with practice to figure this out perfectly. Is everyone fine with this so far? Okay. Shit, my battery's gonna die, so I'm gonna plug in my charger. Okay, so after I'm done this last question, we'll go on break because that's probably the end of this lesson after this. So let me just put myself on mute as I move my stuff and plug in my laptop. Okay, can you guys hear me perfectly fine still? So my next one is I want to basically sketch the graph f of x is equal to x over x squared minus 9. So So I have my vertical asymptotes. So again, that has to do with my denominators, okay? So what would my vertical asymptotes be if I were to factor out my denominator? What would they be? Vertical asymptotes. 3. Perfect. So I got positive 3 and negative 3 because I got x minus 3, x plus 3 because of the difference of squares. So I get x is equal to 3 and negative 3. So those are my vertical asymptotes. Now, what is my horizontal asymptotes? If I divide by x squared, both the numerator and denominator, what do I get? Zero. So my horizontal asymptote is going to be automatically 0. All right. So let's draw what I know so far. So I know at negative 3, I have one vertical asymptote, and at positive 3, I have another asymptote, and I know at y is equal to 0, I have my horizontal asymptote. So now let's find my derivative. So I can know when my graph is increasing and decreasing. So let's find f prime of x. So set that equal to 0. So I know f prime of x, if I were to do my derivative, I would get negative x squared plus 9 over x minus 3 squared times x plus 3 squared. So I set that equal to 0. If I cross multiply, my numerators go away. I get negative x squared plus 9 divided by negative 1. I get 0 is equal to x squared plus 9. I move the 9 over. I cannot have a negative square root, which means it is not possible, which means that my graph is undefined at x is equal to 3 and negative 3. So if I were to draw my sine chart of f prime of x at negative 3 and positive 3, I'm undefined on either one of those. So I need to figure out if I'm increasing or decreasing in those points. So if I sub in a value between negative 3 and 3 and f prime of x, I'm going to get a negative value, which means that I'm going to be decreasing from negative 3 to 3. If I take a x value that is bigger than 3, I'm also going to be decreasing, and an x value that is less than negative 3, I'm going to be decreasing as well. Which means that f of x is decreasing between negative infinity to negative 3, in union with negative 3 to 3, in union with 3 to positive infinity. F of x never increases in this case. Which means there is no maximum or no minimum. So obviously, we can graph this based off what we have so far, because it's going to be pretty easy to determine what kind of graph it's going to be. But we got to figure out our concavity by using my second derivative. Are you guys able to sketch a graph based off the information that we just found? you are able to very, very easily. So I know before we go to that part, let's find my y-intercept. That's when x is equal to 0. So I get f at 0 is equal to 0 over -9, which is equal to 0. So my y-intercept is at 0 and 0. So I can come down here and plot my point. So as you can see, I can probably take a guess as to what this graph is going to look like. So now I need to find my double derivative to find out my concavity. So my double derivative is going to equal to 2x times x squared plus 27 over x squared minus 9 to the power of 3. We can factor it out. So now we need to figure out when f double prime of x is equal to 0. So I said 0 is equal to 2x times x squared plus 27 over x minus 3 cubed times x plus 3 cubed. I cross multiply, so my denominator does not exist anymore. I can divide both sides by 2x, which means that my 2x cancels out. And again, this is not possible because I cannot have a square root of a negative number, which means based on my denominators, my f double prime at x is undefined at x is equal to plus and minus 3. So now I can do my sine chart. So f double prime of x. And it makes sense that my x is undefined at positive and negative 3 because I have vertical asymptotes there. So I found my y-intercept at 0 and 0. I know that at 3 it's undefined and negative 3 it is undefined. So now if I take an x value that is less than negative 3 and plug it into my second derivative function, I get a negative value. If I plug it in between negative 3 and 0, I get a positive value. If I plug it in between 0 and 3, I get a negative value. And if I plug it in after 3, I get a positive value. So I'm concave up between negative 3 and 0 and 3 and infinity. And I'm concave down at negative infinity to negative 3 and 0 and 3. And my point of inflection is going to happen when I sub in 0, which gives me a value point of 0 and 0. It's on Tuesday. Yeah, it has a point of inflection at 0. 0 and 0. So now I know that from negative infinity to negative 3, it is concaving down. I know that from negative 3 to 0, it's concaving up. And from 0 to 3, it is concaving down. So again, based off the information I already had from before, I would have been able to sketch this graph easily. But because we're learning about concavity, I gotta sketch it like this. I could have literally sketched that based off the information I was given to finding the first derivative. And then we have one more example. So take a moment to just copy this down and take in what just happened. And last example, the following graph represents the second derivative. So f double prime of x of a function f of x. So on which intervals is the graph f of x concave up or down? List the x coordinates of all the points of inflection and make a rough sketch of f of x, assuming that f at 0 is equal to 3. So you have our first part written down, f at 0 is equal to 3, which means that it's right here. But for A, I can determine the intervals at which f is concave up. So that means where the double derivative, the second derivative of f of x, is greater than 0. So looking at this graph, when is the second derivative graph greater than 0? Yep, so it's when it's x is greater than 2, or from 2 to positive infinity, it is concave up. Now to figure out concave down, I need to figure out where my second derivative is less than 0, and based off my graph, where is my second derivative less than 0? From as x is less than 2, or negative infinity to positive 2, it is concave down. And because I have a root that 2 means that I have a point of inflection in my original function when x is equal to 2 at some specific y value. My point of inflection based off this graph is at my roots, which is going to be at 2 and some random y value. We don't have to find that y value, which is completely fine, but I can figure out that from 2 and some y value, so let's say here, 2 and y, I am concave down when I'm less than 2, and then concave up when I'm bigger than 2. So that would be my rough sketch of f of x. Again, this is a rough sketch. I was not trying to figure out exactly what this graph was going to look like. I was just figuring out what it would roughly look like given the characteristics of my second derivative graph.